Good morning physicists. In this video we're going to be completing the ray box practical. At some points throughout the video you might want to pause so you can take your notes. First of all, my inquiry question is, how is a ray of light affected when it meets a range of different mediums? Pause now and complete your own inquiry question. Using your understanding of the law of reflection and Snell's law, I would like you to complete the following hypotheses. The materials we'll be using for this practical are a range of lenses, a range of mirrors, a light box, pencil, ruler, power box, and A3 paper. As you can see, we've got some glass lenses with a range of shapes. On the left hand side is a rectangular prism. We also have a couple of mirrors. This mirror here is a plane mirror, which is flat. Two curved mirrors, which can be used as concave or convex. Here we have the power supply and the ray box, which emits the light, and a slit. When I turn on the ray box will emit light, and we can focus that light by using one of our ray slits. The first part of our prac will be looking at the reflection on a plane mirror. Pause now to write down your method. For this part of the prac, we'll be using the single slit. You can see when the one ray reaches the mirror, it bounces off, which is being reflected. If I change the angle of my plane mirror, I'm changing the angle of incidence. Using your understanding of the law of reflection, you should understand that a greater incidence angle will result in a greater reflected angle. Can you recall the relationship between these two? To draw our diagram, we'll trace the mirror and we will then turn on our ray box. To draw the rays, you'll put 2 points on each ray. This allows you to bring a ruler to the 2 points and draw a straight line to represent the ray. Once you've got your points, you'll bring your ruler to the 2 points on the paper and connect the dots to draw your straight line. This will represent the ray of light. Now, something that I've not included on this one that's important to note is that you should include arrows showing which way the ray is entering and which way the ray is exiting. The next step is that you'll have to draw your normal to the mirror. In this case, I haven't measured it, so it might be a little inaccurate. I've continued it back because of the mirror being a piece of glass. It does not actually allow me to trace all the way to the back. Once we have our 2 rays, it's time to measure and compare. Now, if the law of reflection holds, we should see that the incident ray, the angle for the incident ray, which in this case is 30 degrees, should be equal to the reflected ray. Perfect. Now, as you scientists know, we need to test more than once to ensure that our investigation is reliable. So let's try this method again using a different angle. If our method is reliable, we should find that the incident angle is equal to the reflected ray. Let's see how this pans out. Now, you need to ensure you're always measuring the angle to the normal. The normal is the perpendicular line from your mirror. Here we have an angle of, looks like about 48. And on the other side, 48. How good is that? The next phenomena we'll be observing is refraction in a glass rectangular prism. Pause now to write down your method. Once again, we'll be using the single slit and a rectangular prism of glass. To trace this diagram, we want to start by tracing around the piece of glass that we'll be using. Your next step is to turn on the ray box. As you can see at this point, there is no refraction because the ray is shooting directly through. As we increase the angle of incidence, we will see that that refraction starts to show up. Once again, pick 2 points on the ray. And in this case, we can't actually draw through the glass prism, so we put 2 points on the ray coming out of the other side. To draw your line, once again, join the dots using a ruler. That is important, and you can draw your lines. Now what you'll notice with our 2 lines is that if we were to try and draw it straight through the rectangular prism, they don't line up. What that shows us is that there is refraction occurring within the prism. So you connect your incoming and outgoing rays, and that will give you your refracted ray. Once again, you'll be measuring your angle to the normal, so it's important that we make sure that normal is 90 degrees to the surface. Here we have N1, which represents air, and N2, which represents our prism. Measure the angle to the normal and record your angle. As this is N1, we'll be representing this using θ1. We have an angle of 41 degrees. Now you'll measure your refracted angle, once again, to the normal. As you can see, this angle is smaller than our original angle. Now at this point, this is consistent with Snell's law, as it's moving from a lower to a higher refractive index. We should see that the line bends towards the normal. Let's see if the maths holds up. Snell's law states that N1 sine θ1 is equivalent to N2 sine θ2. Our N1 is the refractive index of the incoming medium, and N2 is the refractive index of the medium which the light is traveling into. We can write down our variables. N1 is air, which equals 1. θ1, we have an angle of 41 degrees. Our N2 is unknown, as we're looking to find the refractive index of the prism, and our θ2 is the refracted ray, which is an angle of 26. We can then plug these variables into our formula. Now at this point, you should be able to think back to the slides that I've given you earlier and start to think, what is the refractive index of glass? If you can recall that, you'll be able to compare our final result. So at this point, we get N2 equals sine 41 over sine 26 by doing a little bit of moving around, and we can plug that straight into our calculator. Our results tell us that the refractive index of the prism is 1.496, which is very close to 1.5. That information tells us that it's consistent with our lecture and the material is indeed glass. For the next part of the investigation, we'll be looking at reflection of a curved mirror, in this case concave. Pause now to take your notes. For the concave mirror, we're going to be looking at multiple rays, so we'll switch to the 3-slit filter. This will emit 3 straight rays. I'll be using 2 different curved mirrors, which can be used as either concave or convex. Concave means the inside curved face will be facing the rays. As you can see, when I move it around, there is one consistent point where all of these rays converge. Converge meaning they come together. This is called the focal point. Now I'm going to follow the procedure I did for the last 2 to trace my ray. 2 points on each line, also tracing the mirror, and then we'll pick a point on each other line as we know where the ray meets the mirror. It's important that you remember which dot is for which ray. Arrows, once again, to show the direction that the ray is traveling. Now, when you do some of your own, you'll see that it's not always easy to keep it straight. You could also consider putting a third point, but sometimes using a ruler, the line does not actually go on the dot. Now, what we can see is that all of these rays meet at one point. This is your focal point. What I'm going to use now is a concave mirror with a wider radius. What that means is if we were to do a full circle, the radius of this lens mirror would be greater than the other. And you can see that this affects the focal point. Let's have a go at tracing a second diagram and see if we can measure it. The distance from the mirror to the point where all the lines meet is called the focal length. The focal length of my bigger mirror is 21 millimeters. The focal length of my smaller mirror is about 16 millimeters, not meters. In the next part of our investigation, we'll be looking at the reflection of a convex mirror. Pause now to take your notes. A convex mirror is essentially the opposite of a concave. So for this section, we'll use the same mirror flipped the other way around. You can see no matter where I move the mirror, all of the rays diverge, meaning that they move away from each other. If I'm to bring a plane mirror towards the back, some of the rays that are going over the top are reflected, and we can actually see that we find that same focal point where we were using our concave. This tells us that the focal point of a convex mirror is actually behind the mirror. And you guessed it, once again, we're going to trace our ray diagram. The importance of using a ray diagram is that we can show where rays are predicted to go, and we can also use that information to calculate the focal length of different lenses and different mirrors. In this case, we're going to use that information to see where the focal point lies of this convex mirror. Once again, it's important to note that we use arrows. Now, when I draw my reflected rays, you see that they diverge away from each other. So there's no focal point on the left-hand side. What I can do here is use dotted rays on the other side of the mirror, and that will allow me to find where my focal point is. Where all of the rays meet at one point, that's my focal point. In the next part of our investigation, we'll be looking at dispersion. Pause now to take your notes. White light is actually made up of a range of different colours that travel at different frequencies and have different wavelengths. We can use a prism to split these into their different wavelengths, which show different colours. The reason this occurs is because the different wavelengths have a different refractive index when entering and exiting the prism. For the next part of our investigation, we will be looking at the refraction of a concave lens. Pause now to take your notes. Lenses are an extremely useful part of technology. We see them every day in a wide range of things, most notably your eyes. In this case, we have a concave lens. Concave lens is also known as a diverging lens. As you can see, when I place it in the light on the other side of the lens, our rays diverge, meaning they move away from each other. You can make a ray diagram of this as we did for the last two mirrors. Finally, we'll be looking at the refraction through a convex lens. Pause now to take your notes. Convex lenses are those that you probably see most commonly in day-to-day life. The most common convex lens you use is in your eyeball. Your muscles in your eye are able to contract and tighten, which make a narrower lens, or loosen, which makes a wider lens. As you can see with the first lens, my focal length is about 8 units away from the lens. All of the rays always meet at what we call the focal point. Now, if I place a wider lens, what you'll see is that the focal point is closer to the lens. Now, with our eye being able to tighten and contract means that we can focus our eyes on many different things. That's the end of the investigation. Pause now to complete your discussion questions. Finally, I would like you to complete your conclusion, and that's a wrap. Good job.